Well, welcome again to Algebra and Number Theory, and we've been looking at Pythagorean triples, and we found all the formulae that gives all of these in the previous video, and then we looked at the idea of primitive triads. Well, we can use some of the ideas we've been developing here and also Gaussian integers to push on a little bit, and a similar problem to solving x squared plus y squared is z squared is to find all the families of solutions of x squared plus y squared is z cubed, where x and y are relatively prime and of opposite parity. And we're going to use the Gaussian integers to find a formula which gives the relatively prime solutions to this equation. So we can take this left-hand side here and we can factorize it in the Gaussian integers as x plus iy, x minus iy, and equal to z cubed. Now I want to show firstly that these two Gaussian integers are relatively prime in the Gaussian integers. So suppose not, then any Gaussian prime which divides both of these also has to divide their sum and their product. 2x and 2y. Sorry, sum and difference, I should say. So it gives 2x and 2y. Now, since x and y are relatively prime, then, and pi divides this Gaussian integer, Gaussian prime pi divides these, pi's got to divide 2, and so pi is some unit times 1 plus I, because that's the only factor of, well, a unit times this is the only factor of 2. So then, if we then square this, this has to divide x squared plus y squared, i.e. that says 1 plus I squared divides z cubed. But then, this one here is 2i has to divide z cubed, and that means 2 then is even. But we know that x and y have opposite parity by assumption, so z has to be odd, and that gives us a contradiction. So we can now state that x plus iy, because these numbers are relatively prime, then each of these has to be a cube in the Gaussian integers. So or a cube at least times a unit. So epsilon's a unit and delta is some Gaussian integer. Now if I write delta then as u plus iv, then we've got x plus iy is u plus iv cubed. And if we equate the real and imaginary parts, then we have x as u cubed minus 3v uv squared, and y is 3 u squared v minus v cubed. And then plugging that back in, we get z as u squared plus v squared. So to ensure primitive solutions, we choose u and v to be relatively prime integers, again with opposite parity. For example, if we take u to be 7 and v to be 2, plug that back into the formula, you get x is 259, y is 286. And indeed, if you take that squared plus that squared gives me this number, which in fact is 53 cubed. Now these formulae do not give all the solutions to the equation. For example, if z is 5, we can get the solutions plus or minus 2 plus or minus 11 for x and y, but we can't get the solution plus or minus 5 plus or minus 10, since these are not relatively prime. Working backwards with this, how can we find all the solutions to x squared plus y squared is 3 cubed? First again, we assume x and y relatively prime. They've got to have opposite parity because 13 is odd. And then we get u squared plus v squared is 13. So if we're looking at u squared plus v squared is 13, then the only way that can be true is if u, v are plus or minus 3 plus or minus 2. Plugging that back into our formula from before, we get x and y are plus or minus 9 plus or minus 46. And that gives me some solutions to this one. If x and y are not relatively prime, then we we can only have a common factor. Sorry, they can only have a common factor of 13. So thus writing 13x, capital X is x, 13y is y, then x squared plus y squared is 13, and that gives me capital X. And y is plus or minus 2, 3, so xy is plus or minus 26 and 39. And so that gives me then all the solutions to this equation. So we just observed the equation can be written in this form here. Y squared is z cubed minus x squared. So this in fact is a special case of the Bachet equation that I discussed in one of the earlier videos. Well, just as an example, we solve 1 plus y squared is x cubed. In the integers, well, the conditions for applying the formulae are fulfilled, so we have u cubed minus 3uv squared is 1, and the only solution to that is u is 1 and v is 0, giving y is 0 and x is 1. And that's the only solution where we have 1 plus a square is a cube. Interestingly, if we say 1 plus a cube is a square, then we have more solutions, of course, to that equation. Well, the one application that one can use of the ideas we've been talking about here is an application to Fermat's last theorem for the case n equals 4. And of course, as you'll know, Fermat claimed that x to the n plus y to the n of z has no positive integer solutions for x, y, z for n bigger or equal to 3, and his proof, of course, was proven by Andrew Wiles using some very sophisticated mathematics. Now, Fermat had a proof for the case n equals 4, and I'm going to use the ideas we've developed above to prove Fermat's last theorem for the n equals 4 case. So, we start off with this equation. Let us suppose that it has integer solutions. So if it does, then so does this equation. I can simply put this z to be, I take the square root of this and replace it, and so this equation has solutions as well. So suppose x, y, z satisfy this last equation with z as small as possible. So that's important, and I'm going to get a contradiction. The idea now is to find integers capital X, Y, capital Z that satisfy the same equation now, but with capital Z strictly less than Z, and that'll contradict the minimality of Z. This technique is known as the method of infinite descent and seems to have been first used by Fermat. So we may suppose that these have no common factor and the GCD of x and y is 1. Therefore, that means x squared, y squared and z forms a primitive Pythagorean triple. And then we know what the primitive triples look like, so that means my x squared must be p squared minus q squared, y squared is 2pq and z is p squared plus q squared, where p and q are relatively prime with opposite parity. Now if p, so one's got to be odd, one's got to be even. If p is even and q is odd, then that says x squared is congruent to 3 modulo 4, and that's impossible. So it must be that p is odd and q is even. So I'm going to write q as 2r and plug that in, gives me x squared, putting it back into this equation up here, gives me this, and then this equation gives me this with p and r relatively prime. Now the second pair of these equations implies that p and r are themselves perfect squares because they're relatively prime and they're the square of something, so they must themselves be perfect squares. So I'm going to put p to be z squared and r to be w squared. And then hence, with putting that back in, we have x squared is 2w squared squared equals z to the 4th. Well, that means then we have a Pythagorean triple. X, 2w squared and z squared is a Pythagorean triad, a primitive triad. So once again we can put, without loss of generality, we can put that one equal to p p squared minus q squared. This one is even, so that's got to go with this term here. And then the z squared is that one where p and q are relatively prime. And you should check here that it can't be the other way round, since p and q have opposite parity. Now the second equation gives p and q squares, again gives these as squares. So from this equation here, because capital P and Q are relatively prime, so capital P, capital Q must themselves be squares. So I'm going to put capital X squared as P, capital Y squared as Q, and then they form a Pythagorean, from the third equation we now have x to the fourth plus y to the fourth is z squared. So we get back to an equation of the form we started with, but z squared, chasing it back, z squared is p, and this is the square root of little z minus q squared, which is less than the square root of z, which is less than z because we're dealing with integers, which is less than z squared. So capital Z is less than little z, contradicting the minimality of little z. Well, the next little section's on the sum of three squares. So we've seen that certain numbers cannot be written as the sum of two squares, and there are numbers such as 15, for example, that can't be written as the sum of three squares. We'd like to characterize when a number can be written as the sum of three squares. Now we have a little lemma that tells us when you can't do something. So if x is a 7 mod 8 prime, then x cannot be written as the sum of three squares. So 15 is a 7 mod 8 prime, and this is why it cannot be a sum of three squares, because modulo 8, the square of any integer, can only be 0, 1 or 4. And if you look at all the possibilities here, you can have 0, 0, 0 giving you 0, or 1, 0, 0 giving you 1, or 1, 1, 0 giving you 2, or 1, 1, 1 giving you 3, or you can have 4, 0, 0, and so on. But all you can get then are the numbers 0 to 6, modulo 8, and you can't get 7. Now the full story is given by theorem 10 here. A number n can be represented as the sum of at least three integer squares unless it has this shape. It's a power of 4 times a number of the form 8k plus 7. Notice, of course, if alpha is 0, then n is 8k plus 7, which would be a 7 mod 8 number, and that fits in with what we saw up here. Now I'm only going to prove the result one way. The proof of the converse is very difficult, and most number theory books do not contain it. You've got to search high and low to find a proof of the converse. So I'm going to prove that if n has this shape, then it's not the sum of three squares. So again, if 4 divides the sum of three squares, then if you think about it, either these must all be even, or you need exactly 2 of them odd. Think about that for a minute. So suppose x and y are odd and z is even, then we can write down what their shape must be. Plugging that into our equation, we obtain this. And this then is 2, I'll read this modulo 4, then I'll get a 1 here and a 1 there, so I get 2 modulo 4, but then that's impossible. You can't have the modulo 4, the sum of three squares, being equal to 2. I should say that 4 is a factor of this one. I'm sorry, that's right. So it can't be 2 mod 4, it's got to be 0 mod 4. So hence x, y, and z must all be even. So if n has this shape and it's a sum of three squares, then I can divide both sides by 4, and I can write this down. And because these are all even, these are all integers here. And I could then continue the process until I've eliminated the power of 4 completely, and I simply end up with this is 8k plus 7, but this is impossible by the lemma. The sum of four squares is the following theorem, which is due to Lagrange, completes the story on the sum of squares. I'm not going to give the proof here. Again, you have to look at various books on number theory to find a proof. Many books simply state it. There are various ways of doing this. It can be arrived at from interesting generalization of complex numbers called quaternions. And quaternions, from the quaternions one obtains the following rather amazing identity, which says if you've got the product of two numbers, each of which is the sum of four squares, then you can write that itself as a sum of four squares. So this tells us if x and y are the sum of four squares, then so is their product. And from this, with quite a lot of work, one can deduce the following result of Lagrange, that every integer can be expressed as a sum of at most four squares. And I'm not going to do the proof of that one. Well, we finish off by talking very briefly about Waring's problem. We've dealt with representations of sums of squares. It then became natural to look at the higher order powers. For example, it's known that every integer can be written as the sum of at most 9 cubes. In fact, only the numbers 23 and 239 actually require the 9 cubes, it turns out. So 23, you need all of those cubes to represent 23. In 1970, it was shown that every integer can be written as the sum of 19 fourth powers. At most 19 fourth powers. So, obvious question is, well, what happens when we go higher? So for each positive integer k, I'm going to let capital G of k be the minimum number of kth powers required to represent every integer. Or equivalently, we want the smallest number, gk, such that x equals x1 to the k up to x sub gk to the k to have integer solutions for all integers x. Can we find a formula for capital G of k? Well, no such formula is known, and the problem is often referred to as Waring's problem. We do know the following. G of 2 is 4, that was Lagrange's theorem. So that in fact was theorem 11, not theorem 9, that we proved above. It is known that G of 3 is 9. Every number can be written as the sum of at most 9 cubes. It is known that every number can be written as the sum of at most 19 fourth powers. And we also know that G of 5 is 37. And beyond that, that's all we have. Well, where are these numbers coming from? Well, that, of course, is the unsolved problem, but mathematicians believe that we think we know where it might come from, but we don't have a proof of it. So as we've seen, for fixed k, only certain numbers actually require gk terms. For example, when k is 3, only these two numbers, it turns out, actually require 9 cubes. So I'm just going to pull this number out of the air. I'm not sure who first came up with this, but you take this number, you take 3 halves to the k, you take the integer part of that, multiply it by 2 to the k, and subtract 1. So this symbol square brackets of x denotes the greatest integer less or equal to x, sometimes called the floor of x. Now, just observe that if I put k as 3 into this formula, then I get n as 23, which is one of those funny numbers that actually requires the 9 cubes. This number n then is an attempt to find the worst case for each k. Now, notice that this n is less than, I can remove the integer part, it's less, or perhaps, yeah, it's going to be strictly less than 2 to the k times 3 halves to the k minus 1, which when you simplify, which is less than when you simplify it 3 to the k. So that means to represent n as a sum of kth powers, we need x, this particular n, we need xi to be strictly less than 3, i.e. less or equal to 2. So in fact, we can then count the number of lots of 2 to the k that we need. There'll be that many of them. And then that remaining number, lots of 1 to the k. That is, we can write this n as this number, lots of 2 to the k, plus this number, lots of 1 to the k, and that simplifies back to our n. So this would require that many plus this many terms, and when you simplify that, you get this expression, and that means the g sub capital G sub k must be at least as big as this number here. And I'm going to call this number little l of k. So this looks like it might be the right formula. If you put k equals 2 in, then L of 2 is 4, and that's capital G of 2. If you put the plug in 3, you get L of 3 is 9, and that's G of 3. And that's getting very interesting. If you put 4 in, you get 19, which is equal to G of 4. If you put 5 in, you get 37, which is G of 5. This formula looks like it's working, at least up to here, and it's believed that these two are equal, but no proof has ever been found. And that's the end of this section on Gaussian integers and sums of squares.